At this point, we've talked about how to use the heat of fusion and the heat of vaporization to calculate energy transfers during phase changes. But this doesn't help us explain why there is a change in temperature if you have two different substances being heated on the same hot plate. If no phase change occurs to either of the substances during an example like that one, there has to be some other property of the substance beside heat of fusion and heat of vaporization that can explain a change in temperature. A view of the different variables that we've talked about so far include the variable Q. M and T describes the energy absorbed or released by a substance when heating, and its units are joules. Represents the mass of a substance being heated or cooled, and its units are grams. Don't get this confused if we're talking about a graph of some kind. For example, one that has the units of mass on the x-axis, or the variable mass on the x-axis with the unit of grams, and Q on the y-axis with the unit of joules. If it is a straight, direct relationship line, we would say the slope is also an M. So depending on the situation, you might want to be careful about what the letter M actually represents. T represents the temperature change experienced by a substance. We need to remember that in passing we've discussed that a delta or a triangle represents change. Temperature, a big T, is going to have the units of degrees Celsius. So we're going to take ourselves through a quick thought experiment. If we take a look at beaker number 1, we see that we have 50 grams of a substance and we've heated it so that it has a change in temperature of 10 degrees Celsius. We heated it with Q amount of energy. So this is kind of our base point. The first thing we want to do is take a look at situation number 2. Now we're going to compare situation number 1 with 2 as we have an increase in the mass. We've now doubled the mass of the substance, but the change in temperature has remained the same. What do we think is going to happen to the amount of heat required to increase the temperature of that substance? Make a prediction. If you guessed that it would take twice the heat that it did in scenario 1, you would be correct because we have 2 times the mass, so therefore 2 times the heat. This confirms that heat is directly proportional to mass. For this next one, we want to compare scenario 1 with scenario 3. In this case, we have the same mass of the substance present, but we've now heated it up 3 times the difference in temperature. So what do we think is going to happen to the amount of heat required to change the temperature of that same 50 grams of substance? Make a prediction. If you thought that we would need 3 times the heat that we initially would have needed, you would be correct. This confirms that heat is directly proportional to the change in temperature. If we triple the heat, we can triple the change in temperature. What I want to look at is comparing what if we change the mass and the temperature together. So compare 1 and 4. If we have double the mass and triple the temperature, what's going to happen to the amount of heat required to make this happen? Make a prediction. If you said that we would require 6 times the heat, you're right on track because we both doubled the mass and tripled the change in temperature. At this point, we've recognized that there is a direct relationship between heat energy added and the product of the mass times the change in temperature. So if there's a direct relationship, if we were going to graph those two values on a graph, we would find that that line would be a direct positive slope. So when we look at that slope of that line, we can predict the units of that to be y over x, joules divided by grams times degrees Celsius. This slope represents a new constant, which we can include to create a relationship or an equation between Q, M, and delta T. actually create an equation to set Q equals to the mass times the temperature, we need a proportionality constant, and we call that proportionality constant the specific heat capacity. The specific heat capacity is that proportionality constant that tells us how much energy is required to change the temperature of 1 gram of a substance by 1 degree Celsius. If we were to compare the specific heat capacities of water and of oil, just like in one of the examples we have seen in class, we could see that one of them is greater than the other. In fact, the specific heat capacity of oil is much less than that of water. So its temperature changed much more drastically than the temperature of the water. The oil increased its temperature very, very fast, where the water did not increase its temperature as fast. So that is how we found our specific heat equation, and we can use this for some future examples.